In Module 14F, I want to go ahead and introduce the other colligative properties we're going to deal with, which are freezing point depression, boiling point elevation, and osmotic pressure. Again, all four of these, vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure, are colligative properties. You need to be able to understand these properties, and then in a future module, we're going to actually work a bunch of calculations with them as well. Again, as a reminder, colligative properties are number dependent, not identity dependent. It depends on how many I have of something in there, not what that species is specifically. So we're especially interested in colligative properties. Colligative properties are defined as properties of solutions that depend on how many solute particles are dissolved, not the identity of the solute particles themselves. If I go to say I drive to the library and I'm dropping off books outside at the outside drop-off, the drive-up drop-off. It doesn't much matter to me if it's, what type of vehicle in front of me there is. It depends on how many vehicles there are in front of me. I've gone up to the drive-thrus at the drop-off at the library and there's been no one there, so I'm able to drop off my books very quickly. I've gone before and there's 4 vehicles in front of me. It doesn't matter if one is a tiny little car and one is a giant truck. Yes, they take up a different amount of space, but they're all one vehicle. They all drop off their books, then I go up as well. It all depends on how many books are they dropping off, not what book are they dropping off. So again, depends on how many, not what it is. Colligative properties are properties that we find in solutions, vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure, that are dependent on the number of solute particles, not the identity of those particles themselves. So first, let's talk about boiling point elevation, or BPE. The little graphic here, friends keep you cool. These guys make it harder for me to reach my boiling point. Boiling point elevation is harder for students to kind of wrap their head around. So for this, I need you to remember the definition of boiling point. Boiling point is the temperature when the vapor pressure of the liquid equals your external pressure. So if you have a non-volatile solute, here's your solvent, here's your non-volatile solutes you're adding into it, or solutes in general that you're adding to it, the vapor pressure of the solution is now less than the vapor pressure of the solvent. We've just talked about this in the previous module. If I have a volatile solvent and a non-volatile solute, the overall vapor pressure of that system will be lowered. Now, the vapor pressure is lower. It's harder to reach the atmospheric pressure. Therefore, I need a higher temperature to allow those particles to escape so that I can reach the atmospheric pressure, hence the boiling point has been elevated. The lower the vapor pressure, the higher the boiling point. The vapor pressure of a solution is lower than the pure solvent, so the boiling point must be elevated to reach that atmospheric pressure. These are the 2 equations we have for the change in temperature, specifically boiling point temperature. TB is boiling point temperature. KB is a constant. M is molality. We have to use molality for boiling point because it is a temperature measurement. And molarity is temperature dependent because volume is actually temperature dependent. And I, we will talk about the next module as well, is called our Van't Hoff factor. And that takes into account how many particles do I have. So what this is calculating is the change in the boiling point, and that is equal to K sub B times M times I. Again, we will talk about I in the very next module. We'll do a bunch of examples with it as well, but molality you already know how to calculate, and then K sub B is a constant. The biggest thing to note here is that this calculates the change in boiling point, not the new boiling point. So we know water boils at 100 degrees C. If I have a solution with water, I expect that boiling point to be higher. Say that the boiling point actually ends up being 100.7 degrees C. What this equation is going to do is it's going to give me an answer of that difference. It's going to tell me 0.7 is my change in temperature. I then need to add that to my boiling point to find out my boiling point of my pure solution or pure solvent to then figure out what the boiling point is of the solution. So please note that this means change in. This is not your final temperature. It is the change in temperature that you will then add to the boiling point of the pure solvent. We also have freezing point depression. Freezing point depression, friends keep you from freezing. They're going to lower your freezing point. It's harder to freeze. Something melts where it freezes. Let me go back to this, just because students tend to forget this. Something boils. Boils meaning it's going from the liquid phase to the vapor phase or liquid to gas phase. This is at the exact same temperature that something condenses and goes from the gas to the liquid phase. If you're looking at freezing point depression, this is your melting point or freezing point. Something melts where it freezes, meaning the temperature is the same. It's harder to freeze things. It lowers your freezing point. I'm from Minnesota. My grandfather worked for the city I grew up in my entire life, the city of South St. Paul. He worked for them, for the city, and he drove the plows, he drove the salt trucks, he did the roads retarded the roads in the summer, etc. I actively remember being woken up in the middle of the night by phone calls telling my grandfather he had to come plow. It was his favorite job. He loved it. But then he'd also have to drive the sand truck. We put sand and salt truck. We put sand down on the roads on the ice to get gription or to get some kind of surface to, there that we can actually grip to so they're not sliding on ice. But we add salt to the roads, and even within our own walkways and stuff, we add salt to make the ice melt faster. It melts below its freezing point. Freezing point depression. It's going to allow us to reach that point faster. Freezing point's a little bit easier for students to think about. What I want you to pretend you have is pretend you have a grid. And within this grid, you've got these common shapes. Let's pretend that you've got all these squares that are fitting in very, very nicely together. But I'm going to come in here and I'm going to put a random shape in here that's going to disrupt part of my grid. This piece in here, this piece I've added in here, this solute that does not match the pure, now disrupts my entire system. Now this is over here, this is up here. This one can stay the same. This one can stay the same. This can stay same. This can stay the same. This can stay the same. This is now altered over here. It has disrupted the connection points between these species. They do not tie together as nicely as they did before because now they've got a solute in their way. It's disrupted the crystal structure. Doesn't matter what it is, matters how many I have. How many things have disrupted that crystal structure? If you put all of, if say you have a bunch of books and they're all the exact same size, they fit very nicely in the bookshelf. What if you have two books that are not the same size, but they're smaller? They're quite obvious in that bookshelf they're not the same size, right? It doesn't matter what they are, it just matters they're a different size and they're disrupting the structure or the compactness of that system. Freezing point depression is the same kind of concept where these solutes get in there and they're not the same size, they disrupt the crystal structure. When they disrupt the crystal structure, the intermolecular forces holding your pure solvent together cannot be held quite as tightly. It's interrupting your intermolecular forces, interrupting that crystal structure. It's causing defects in that structure, which then mean that it's going to take less energy for me to break it apart and melt that sample. That less energy leads to a lowering of the freezing point. It melts faster. The equations we use for this, delta T equals K sub F times M, or delta T equals K sub F times M times I. I recommend, honestly, for boiling point and freezing point, just remembering the one equation. For boiling point, of course, that would be delta TB equals KB times M times I, because sometimes I is 1, sometimes it's not. and we will again talk about that in the next module. But if you can remember that one equation and substitute in either Kf or Kb, you should be fine. Also realize that this is calculating the change in temperature. So it's going to give you a small value. You then need to subtract that value from the actual freezing point of the pure solvent to figure out the new freezing point of the mixture. Here's a nice just graph from your book kind of showing you the same thing. Why does solute raise boiling point but lower freezing point? So you're adding a non-volatile solute. Adding a non-volatile solute lowers your vapor pressure. So now at a given any given temperature, any given pressure, the temperature must increase to reach the new vaporization curve line. At a given pressure, the temperature must decrease to reach the new fusion curve line. Remember, fusion is melting. So on the curve here, we see the pure solvent line here in blue, and then the solution is listed here in this red color. So the melting point of the solution has been lowered, whereas the boiling point of the solution has been increased. Here's a nice little chart from your book that just shows you some common freezing points, boiling points, Kf and Kb values. These will always be provided to you on any assessment, but that does not mean they'll be provided during homework. So, and you should just absolutely memorize these two values. We use water a lot. You need to just know those values for Kf and Kb for water. You should also know that the normal freezing point of water is 0 degrees C and boiling is 100 degrees C. So this bottom line here, or this bottom part of the chart here, you should absolutely just know, but the rest would be provided to you. We also have osmotic pressure. So another thought experiment here. Osmotic pressure. If you have a solution that has pure water on one side, and on the other side, we have some solution. What's going to happen over time? Over time, what's going to happen is that the height, we see here, change in height, of one side is going to increase. The particles, what we have in here, this part separating the two, and why is it going one direction? The part separating the two is a semi-permeable membrane. Sorry, that word's hard for me. A semi-permeable membrane is a membrane that allows some particles to pass through, but not other particles. So for example, in the diagram here, we have it set so that it will let water molecules pass through, but not the solute particles. So these water molecules, if we look in here, looking a little closer, we can see the water molecules are going both directions. They're traveling back and forth. But none of the solute particles are able to do that. Only the water molecules are traveling back and forth. If I let this sit, initially it's going to have, equal height on both sides here. Equal height both sides. But once I reach an equilibrium, I see that it's higher on the side with the solute than it was on the side with the water. Why is the water all traveling to the side of the solute? Well, what's happening here, because the water can only the water can travel back and forth, on this side of the membrane, it's more likely for the water to reach that membrane. On the other side, it's less likely. So I've got only water particles here, and they can pass through. Over here, I have a mixture of water and solute particles, but only the water particles can pass through. If they're going to pass through at an equal rate, per se, meaning water that can pass through either way, what's the likelihood of water passing through this way? Pretty high. It's the only thing on that side. Water's the only thing that can pass through. Water's the only thing there. The only thing hitting that membrane is a water particle. So therefore, it's likely that the water's going to pass through that direction. Going the other way, though, if I just look at these first, the first part of the molecules really close to the surface here, I've got 2 solute particles and 2 water molecules. Only half of those particles can actually pass through. So just by statistics, it's less likely for the water molecules to come back than pass through as they already have. So what happens is more water molecules pass through to the side that has a solution, while less water molecules pass back to the water-only side. Osmotic pressure is the pressure required to prevent osmosis from occurring. We write this as pi. Why? I don't know, but it is. It's pi. So again, the pressure required to prevent osmosis from occurring is your osmotic pressure. Osmosis is the net flow of the solute molecules through that semi-permeable membrane from the less concentrated side to the more concentrated side. So osmosis is when they're going to the more concentrated side. Osmotic pressure is the pressure that's required to prevent that from occurring. We're measuring what is that pressure. And I know a lot of you guys are biology majors or on the biology track, so you have a lot more use for osmosis. Truthfully, I'm not a biologist. It doesn't work in my head as well. But saline solutions work this way, and even though I don't eat them, I'm a very picky eater, I found out that this is actually how pickles are made through osmosis and osmotic pressure, concentration gradients, and a brine or heavy salt solution. Here are the equations for osmotic pressure, though. Pi equals MRT or pi equals MRTI. I recommend just memorizing this equation and then realizing that sometimes I is 1. Pi is your osmotic pressure in atmosphere. Capital M is your molarity. R is your gas constant, and T is temperature in Kelvin. Hopefully you also recognize that this is the same as PV equals nRT, rearranged. It's pressure. Of the 4 colligative properties, osmotic pressure is the most sensitive.